So we spent quite a bit of time talking about special relativity, how motion, uniform motion, will cause a curvature of space-time, that length will contract and time will dilate. And prior to that, we spent some time talking about what Sir Isaac Newton had to say about gravity. Now we're going to start putting this together. Recall that when we first started talking about dark matter and dark energy, when we first started talking about the evidence for dark matter, we talked about the curvature of space-time and how that is related to gravity. So this is what we're going to do here. When Albert Einstein came out with his special theory of relativity, which we've just covered, that was in 1905. Again, he was speaking about uniform motion. That's just constant velocity, like cruise control. But that's not the only kind of motion that there is. There's also changing velocity or acceleration. Einstein realized that he needed an overall general theory to cover all aspects of this curvature of space-time. And 10 years later, in 1915, came his general theory of relativity. Here's one of the ways that we can approach this idea. On page 58 in your book is a very simplified drawing. You don't really even have to take notes with this, but let me just walk you through this. So this will be a thought experiment. We're going to have a rocket ship that's going to take off, and it's going to accelerate. It's going to increase its velocity as it takes off. And for the purposes of this thought experiment, we're going to slow down the speed of light to a snail's pace. Now, we've been taught since grade school that light travels in a straight line. And so it does, sort of, but you'll see. So as we observe what happens, we see the little photon come through the little round window in the spacecraft, and that asterisk represents the photon. The spacecraft begins to take off. It moves upward, but look where the photon is relative to the window. Now it's going even faster. Look where the photon is. And even faster here, and look where the photon is. But relative to us, the observer, that photon's traveling in a straight line. But if you look at the trajectory of that photon from the perspective of the interior of the spacecraft, you would see that it would follow this sort of a pattern. Kind of like if I took the laboratory rock and just kind of gave it a little shove like so, it would have that curved trajectory. Now, here's a little bit of Sir Isaac that everybody walked in knowing. An object in motion stays in motion until acted upon by an outside force. Everybody knows that. So that is why, back to the laboratory rock, on one hand, I should be able to toss the little laboratory rock and have it go in a straight line, but it won't. Why? Because of gravity. And it will form exactly the same trajectory as is described here. Einstein puts all of these ideas together. In a thought experiment like this, we can see how we can invoke a curved pathway for a photon. We also know that the effects of acceleration due to a change in motion are indistinguishable from the effects of acceleration due to gravity. Einstein reasons then, shouldn't gravity also affect that pathway? And it turns out he's absolutely correct. That gets us to the next page, page 59. The problem with Einstein's theories is that it took a long time for technology to catch up with what he had to say and then put his ideas to the test. But this is one of the first things that was tested. And how were we able to do it? Well, the idea goes like this. Let's say you have a star, a distant star that is light years away. And here's the sun right here. And here we are on planet Earth. the idea is that the light from this star travels through space in what we would call a space line until that light, that beam of light, gets near the sun. Then the sun curves space-time and therefore curves the pathway of the light. Well, how can we test that? Well, it turns out that here on planet Earth, we're very fortunate. We have a single satellite, the moon, that is just the right distance and just the right size so that periodically it will get exactly between us and the sun, and we have what's called a solar eclipse. Now, in a total solar eclipse, it really does get so dark that we can then see the stars. And here's how the experiment worked. As the idea is that at the sun, in the middle of eclipse, would be moving through the sky, and you'd be able to see a star right next to it, and then it would cover the star, and the star would then come out on the other side. This experiment was done by an English astronomer known as Sir Arthur Eddington. And this experiment took place in the late 19-teens, early 1920s, thereabouts. And they set up this experiment, and the idea was that if that light was curving like so, then the time between when the star disappeared, being covered by the eclipsed sun, and the time that it reappeared would be shortened, and that the star would reappear sooner than it ought to. If the light was in fact going in a straight line like so, then it would take longer to see that star come out again. Turns out the star did reappear sooner than it ought to. Not quite exactly as Einstein had predicted, but pretty close. They contacted Einstein about the results, and he went and checked his math, and he says, oh, I guess I forgot to carry a 2 or something. He'd made a math mistake. He fixed the math, and then it dialed right in. So this demonstrated, this little experiment was actually a major experiment that clearly demonstrated that the pathway of light is space, and if you curve that pathway, then you curve the pathway of the light itself. It proved the curvature of space-time. It also, interestingly, resolved another mystery, or if you want to call it that, or some might say an embarrassing exception, that had been hanging around since the time of Sir Isaac Newton. Sir Isaac Newton, as we've talked about, came up with his theory of gravity, came up with his version of Kepler's third law, and when you apply the theory of gravity, when you apply Kepler's third law to orbiting objects, it works beautifully, but it didn't quite work for planet Mercury. Why? Well, Mercury is 1/3 the distance between us and the sun. That means that using the inverse square law, that means that by being 1/3 the distance, Mercury is on the receiving end of 9 times the sun's gravity that we are. That is a whole lot of gravity. That's a whole lot of space-time curvature. And once you made an accounting for that space-time curvature, then the orbit worked out just perfectly every time. It also gives us this, which we've talked about. Gravitational lensing. And one other thing about how gravity affects space-time, we've been kind of focusing on the space part. It also affects time. The nearer you are to a gravitational source, the slower time is. So for us here on planet Earth, clocks are going a little bit slower than they would be, say, 1,000 miles above the surface of the Earth. All right. In fact, clocks at sea level are ever so slightly moving slower than clocks on the top of Mount Washington. Even that difference will make that difference. And so gravity does affect time as well. Later on, when we talk about black holes, this will make a little bit more sense when we say that from the observer's point of view, as you approach a black hole and get to what's called the event horizon, when you hit that event horizon, time stops right there. Time comes to a dead stop. But that's for another discussion. All right, so we'll pause here and go on to the next topic.